Hey, how you doing? Now that we're recording, it's good to see you all. All right, so today, an extension of volumes. So we've been spinning volumes around axes a lot, and we should feel pretty comfortable and confident with that now. We're going to create volumes in a different way now, and I always wonder if I should start with this way or end with this way, and you can tell me when we're finished. Some students actually think that this is a little bit more straightforward way of starting volumes, and other students find it a little bit challenging because we're not just doing pi r squared anymore. We're not just doing circles. So, for example, we're going to take this circular base, and we're going to build squares on it. So everywhere you could draw, and the square is going to be perpendicular to the x-axis. All right, so we're going to build squares on top of this base, and I'm going to try to show you what it's going to look like, and then we'll actually find the volume, and then we'll do a couple of these. Okay, so the first thing that's important is you have to sort of envision the y-axis being dropped so that you have a three-dimensional base. So what we're trying to do here is show you that this is the bottom of whatever it is we're building. Is that okay? All right. And on that, every place we're going to build a square. So let's see. If I go, I'm going to try to do it really poorly, and then we'll get the computer to do it. So from here to here, I'm going to build a square that's going to stand upright like that. Okay. Now, what happens to these squares as I get closer and closer to the diameter? They get bigger and bigger. Think about the square here at the diameter. You know, it's very, very tall. Okay. And if you can sort of imagine, those squares, they're going to leave like a ridge down this side, and they're going to leave another ridge down this side. So it's going to look something like, I don't know. Oh, the back. All right. Now there's going to be no, not the flat screen. Now there's going to be another half of it, right? And I don't know how many TVs have circular bases, like at the bottom, but maybe it's a good start. Okay. Now, instead of my lame drawing, let's actually show, here's what the squares look like, right? As they go across, they get bigger and bigger and bigger. And then let's just actually show you the solid. Oh, it's going to take forever to create it. Let's just show it. Nope. There we go.
Looks like an opera house.
Oh, the Sydney Opera House? Or is that? No, okay. So here it is, and if we did, we could show you this. Oh, that's not what I want to do. Oh, yeah, it is. You can see how every time we slice, we get a square. Okay? And the bottom is a circle. And so this is actually a very interesting shape. Like, I mean, I don't really know how many of these you come across, so I don't know. Is it like the Pope's hat or something? Maybe? No? A bishop's hat? I don't know. Like something?
Is that not going to be accurate? An inverted fortune cookie. What? I see that. Yeah. It's filled in the... Yeah.
All right, so we got two people that agree on an inverted fortune cookie. I don't know about that.
Wait, hold on. But is it not going to be accurate? It's like you turn up and circle and it doesn't work.
Say that again?
Like, do you see how on the edges the square doesn't like match up with like the edge of the circle? Like, so how does it
I think it matches up.
No, but like the circle is curvy, the square is straight.
Yeah.
You end up with a gap between the edge of the circle and the first square.
No. They just didn't draw it in. Here you'd have just a smaller square, a smaller square, a smaller square, right? Okay. So here, let's hold on. So they didn't draw it in, but there are squares here, and as a matter of fact, they get teeny tiny to the point where that square is actually a point, which is sort of weird, right? The square converges on a point. What do you have?
So you see the curved part of the 3D graph?
Yeah.
Is that like the same dimension? Is that like the same size as the circle base? Or
No. I don't even think that this is circular.
No. Like semicircular.
I think it might be parabolic. I'm not sure. I'm really not sure. I don't know. That's an interesting question. Dan's saying, if you were to lay this in the XY plane, what would the equation of that be? I don't know. But it's definitely not this, because if we were to take this and rotate it up, it'd be a hemisphere.
But the base is a circle, though.
The base is a circle. All right, so what does it look like?
Pringles can. The little baby side.
Yeah.
Have they like?
Oh, yeah.
Inverted portion cookie works so much better.
Wait, a Pringles
The
can.
like little small Pringles.
Pringles can looks like this.
No. The ones you
They're
take to
small
school when you're really little. They're like plastic.
Don't they look like this?
There are other ones.
All right, sorry. I'm old. Okay. Okay. All right. So we're going to work on finding the volume here. And let's actually, this goes from 2, and that's 2. So instead of R, we're going to focus on it being 2. So I'm stacking squares this time. Instead of stacking circles, I'm stacking squares. And I'm stacking squares, you have to ask yourself, along which axis? The x-axis or the y-axis? So I'm stacking them along. I don't see that. I see that as stacking them along the x-axis, right? I have all these. They are parallel to the y and perpendicular. And that's actually, you know how you sort of had keys as to whether it was going to be dy's or dx's when we were going around axes? The same thing's going to be true here. If you're perpendicular to an axis, that tells you what you're going to be. So if we're perpendicular to the x-axis, that clues us in that we're going to have a dx. All right? So where are we stacking on this circle along the x-axis? Where are we stacking all these squares? And in this case, we said r was going to be 2. So from -2 to 2, guess what I'm going to do? I'm going to double from 0 to 2. I don't think so. I'm going to do that, though. I'm just not there yet. All right, now, I think I'm going to go back up here to this picture. And here's what I have to figure out. I know what the area of a square is. What's the area of a square?
R squared.
Side squared. Okay. That's different from pi r squared. This is just s squared. That's what the area of the square is. So this says, hey, add up all of the squares from 0 to 2 that have an area of s squared and a thickness of dx. Problem? Yeah. Okay. So we can find s. S is this whole distance. All right? Now, if I were to ask you what just that distance is, what would you tell me that distance is? Who said it? Alicia? That's a y value, right? Isn't that a height above the x-axis? So s has to be 2y. And they gave it to us in the problem. I apologize. They told us y was equal to 4 minus x squared. So we actually we know that the side is equal to 2 times 4 minus x squared. And if I go back down to my formula, hold on, I should stop. That was actually the trickiest part. That's the hard part. So I need to slow down.
Remember we dropped the y-axis down?
Right, so this is the y-axis, this is the x-axis. Any distance above the x-axis we call y.
Oh, right.
And they give you what y equals, right?
And they told us this. They said, hey, the base is defined by y equals root 4 minus x squared. And then I said, okay, well, the side is double that. The side of every square is going to be twice the y value. And what is the y value? Root 4 minus x squared. Do you want to ask any more questions? That's the hardest step. It really is. Deciding if it's dx's or dy's, you can tell by what it's perpendicular to. Deciding what the area is, they're going to tell you. You're going to have squares perpendicular to the x-axis. You're going to have semicircles perpendicular to the y-axis. Like, they're going to tell you what you need to do. The hard part is finding out how that relates, how the x or y values relate to the area that you want. And in this case, we know that 2y is equal to 2 times square root of 4 minus x squared. So now I can say from 0 to 2, 4 minus x squared, quantity squared, dx.
Why isn't this the area?
You sure?
Yes.
And I'll do a little bit of algebra. If I square it, I get 4 times 4 minus x squared. And now you could distribute and do each piece. I think I'm going to leave it at that because the calculus part, oddly enough, is the easy part now. It's actually all the geometry and the setup part that's hard. Definitely. You want to ask a question, though, or just see another one? Go ahead. That I could have, if I wanted to, I could have done stacking squares from -2 to 2 along the x-axis, but I know that when I actually have to do the calculus, plugging that 0 in is going to, it's like a lazy factor, right? Plugging 0 in is going to be a lot easier than plugging -2 in. Any more? Yeah. Any more questions? I mean, we're going to do at least one, hopefully 2 more. All right, we should just do them. All right. So let's take a look at 17 from your homework, from your classwork, rather. Sorry. Again, we have squares. And it says the base of a solid object is the region enclosed by 1 over x, y equals 0, x equals 1, and x equals 4. So, just to give you an idea, x equals 1, 2, 3, 4. Okay. That's the base. That's the bottom of what I'm building on. Okay? I'm going to try my best to tilt the axis and draw it so that's the bottom, and I've tipped it. I've tried to tip it so you can see that that's the bottom. And it says every cross-section perpendicular to the x-axis, that's a clue, is a square. All right, so it looks like that's going to be a square, and the square up here is going to be bigger. And then there's probably going to be some squares in the middle. So it looks to me like this thing is going to, whoops, looks something like this. So it's going to be like, all right, so like a quarter pipe that gets a little narrower as you get down to the bottom, or like some sort of, I don't know, you could crawl in it and check it out. Be this, I don't know, couldn't you like crawl in it? It looks like a duct that gets bigger and bigger. Yeah, all right, fine. Before they invented circles, right? It's a square megaphone. I'm going to try my best. So here's, I did this in not Sketchpad, but another program, and here's sort of what it looks like, right? So you can get an idea of that shape. You see, like, it has a square end at one end. Hello down there! Right? Yeah, but the hallway gets, like, does a little...
Hallway,
Okay, yeah, it's a Willy Wonka hallway. I love it. Okay. So is that okay for what it sort of looks like?
That's really cool. How do you do that?
There's a program called WinPlot, and I think it's actually the folks up at Exeter. Didn't you do that? Did you Exeter?
It's actually
Andover, sorry. Maybe it's the folks at Andover. They put out like this free software, and it does some pretty amazing things. So let's see. Let's go back. So we have an idea of what it's going to look like. So let's see. I know I have squares. So the area for a square is s squared. Dx or dy's? Dx because it's perpendicular to the x-axis, or you can think about it as this little thickness is dx. All right, so if I know it's along the x-axis, going from 1 to 4. Now, there are still 3 out of 10 calc students that always want to put a pi out in front. You get so used to doing circles that if you do anything else, you get a little freaked out. So it's not always going to be circles. In this case, it's squares again. We'll do another one where it's semicircles, I think. And this is what's going to annoy you. What's going to annoy you is that you can change. You could build squares. You could do the same problem with semicircles. You could do the same problem with isosceles triangles. Instead of squares, you could build triangles on top of that. And you're going to be frustrated by the fact that we can't do every possible kind of geometric shape that we could build on that. Certainly, I'm going to try to show you as many as I can, but there are going to be problems like, for homework or review or whatever, they're going to be like, hey, try doing this one. And you're going to be like, I've never done that shape before. And that's okay. All right, so from 1 to 4, s squared dx, I need to figure out what my side is. Well, that's the length of my side. What kind of value is that length? That's a y value. So in this case, actually, my y is equal to s. Not 2y, but all I need to do is 1 to 4 of y squared dx. And that, guess what? They told me what y is. So 1 over x quantity squared dx. And I'm going to leave it at that because, oddly enough, it's easy. It's just calculus. Right? I mean, it sounds funny, but actually the setup's really the hard part. Once I get you to the place where all you have to do is calculus, you guys are probably fine. All right, we're going to do another one, but do you want to ask a question? All right, I'll take your silence to mean no. All right. Working backward. The base of a solid object is the region bounded by a parabola and the line y equals 2. All right, so I have this parabola, and I have the line y equals 2. So that's what the base is going to look like. All right, so I'm going to try tipping this. This is going to be hard. Maybe something like that. Maybe that's what the bottom's going to look like. And I tried to tilt it down. And this time, every cross-section perpendicular to the y-axis is a semicircle. So, let's see. This is my y-axis. So, every time I go perpendicular, I'm going to get a semicircle. Yeah, all right, half an igloo. Because this side right here is flat, right? Let's see. I think I messed up when I tried doing it on WinPlot, so let me try again. All right, so we want y equals, what was it, 0.5 x squared, right? Okay. And the equation y equals 2. Okay. And now we want to do sections, cross-sections. And I want to do semicircular, really? It'll only do it it'll only do it on the x. That's a bummer. All right, wait. Hold on. Nope. Shoot. Wait. Okay, hold on. I have an idea. What if I do file equation? If I do an implicit, if I do x equals y squared. Okay. All right. So I need to hide that.
2y squared?
Yep. Is that what I need? All right. Oh, shoot. What just happened? Oh. No, that didn't work. Is that right? Maybe it is. Okay. And then the line x equals 2. So let's see. We need a new equation. X equals 2. And now let's see if I can build it. I don't know. I hope we can. Oh! It won't let me do it with explicit. I'm really bummed.
Why did the builder fail us?
Ah, that's such a bummer.
You 0.5x squared minus 2, and then you rotate around the x-axis and over.
Say that again?
If you do 0.5x squared minus 2, and then rotate around the x-axis, that would be the same shape.
But I'm not rotating it.
How do you do that?
I'm building semicircles on it.
Oh.
That's my problem. All right, so I'm going to admit defeat, at least for now. I know. So you have to deal with my, lame drawing. And look, the idea is that everywhere along here, these semicircle slices, right? Ooh, that's getting worse and worse. All right, let's see if we can trot our way through it. So, dx's or dy's? dy because I'm stacking along the y-axis. From where to where on the y-axis? 0 to 2, because they told me that. Now, what's the equation for a semicircle? 1/2 pi r squared. So whatever your area is, that goes in here. All right? Now I have to figure out what r is. Well, all right, you're ready for me. R is an x value. All right. Well, we know a relationship between x and y. So I guess x is equal to...
I got
root 2y? Okay. So, from 0 to 2... Now, if you want, you don't have to. You can bring the 1/2 pi out in front, because they're just constants. And then I need to take root 2y and square it. So that's just going to be what? 2y. And it's just calculus from there. Okay? So, can you see how in some respects this is actually maybe a little easier than rotating around like the x and y axis? Okay. Well, there are definitely some students that like this much better because it's much more straightforward in some regards, but the hard part, there are some students that don't like it because the hard part is you have to know your area formulas and you have to figure out what that area formula is in terms of x or y. All right? So I think you have... can I see your blue? So, let's see. Like tonight there are, well, yeah, I guess 3, but one has 2 parts. So, semicircles and squares. Number 2 is semicircles. Oh, yeah. And then number 3 says isosceles right triangles. So that's the little bit of a stretch one. Okay, that's one that you haven't seen, but like if you think about isosceles right triangles, you should know a little something. 1/2 base times height, but what do you know about the base and the height? They're the same, and one of these is going to be on the base, right? So it's going to be an x or a y, I guess.
So it's 8.2z.
Yeah, sorry, that's wrong. 8.2D. And I think, Alicia, that gives us a couple minutes to squeeze in 6. Is that, you're feeling all right about it? Does anyone else want to talk about 5 or 6? Is there a consensus? I don't think we'll have time for both, but if there's a consensus, I'd be happy to do.
Yeah, 6 is harder.
Why don't you,
Yeah.
Let's do 6.
well, then will someone talk to Katie about 5 at some point? Okay, no, that is so lame. Like, really? No one's going to say, yeah, sure.
I mean,
I'm not saying it's easy.
I don't think 5 is easy.
All right, well, thank you, Alicia. All right, so, let's see. 6, first quadrant region under the graph of 4 minus x squared, that's going to be something like that, is rotated around the line x equals 3, right? Thanks. So we take that and we rotate it around x equals 3. I think we're going to get something that looks on the outside sort of cylindrical, and on the inside
it's a football stadium.
With a hole in the bottom. So I definitely wouldn't want to, like, I don't know. Yeah. I guess, I don't know, you just slide down. What? Alright. Where you can go in anywhere and then... Alright.
Yeah.
Alright. Discs or washers? Pi. DXs or DYs? DY because it's parallel to the y-axis. And where am I stacking them then if I'm going 0 to 4? Okay. So now I need to tackle the radii, and one of the radii is a piece of cake because it's always the same. Which one is it and what is it? The big one. And so who said the big one? Alicia said the big one, and Morgan said 3. So the big radius is always 3. So that's 3 squared. Now, I have to take care of this little radius, and the little radius is always changing. So let's see. I know the whole thing is 3. And I know that this is what kind of value? That's an x value. So r is equal to 3 minus x equals r. I mean, you can say 3 minus r equals x, but we don't really care. We want to know what r is equal to. R is equal to 3 minus x. So you could put 3 minus x quantity squared there, but the problem is we need x in terms of y. Did they give us anything like, what do we know? Y is equal to 4 minus x squared. So let's see. X squared is equal to 4 minus y, and x is equal to root 4 minus y. Well, so this one's different. That's actually a really good question. So I'm not just squaring the x. This is actually pretty ugly. I have to square the 3 minus root 4 minus y. So, like, I would actually have to first outer inner last. Like, I'd have to distribute that all out. And then I wonder even if I have a shot at using... Oh, yeah, maybe I do. I guess you could do that by hand. All right. You can if it doesn't say use the fundamental theorem. If it says use the fundamental theorem, then they're implying that you need to do it out. And certainly, you're going to be asked to do that sometime. Not all the time. Like, there are going to be some times where the point of the problem is just to be set up, and I don't care how you get the answer. There are going to be some problems where the point of the problem is the setup, but also doing the calculus to make sure you haven't forgotten all your anti-differentiation and algebra skills. All right? So, again, I'll readily admit, like, questions like this, these are the hard problems because the radius, you have to actually think about what the radii are, and that makes them a little bit of a challenge. Maybe. I don't know. I haven't done it out.
Root 4 minus y.
So you're going to get what? 6 minus 6 root 4 minus y. Oh, maybe you're not going to be able to do that by hand. Oh, that piece you're not going to be able to do. You're right. Yeah, hold on.
Which is why the answer in the back of the book is considered.
What was in decimal?
No,
No, there was just that setup right there. That last line.
Oh, what did the problem ask you to do? Did it say just set up?
No.
It said find the volume, but the answer was I.
Ah, the answer in the back of those books. Those people who write those answers, my gosh. So this would be 9 minus 6 root 4 minus y plus 4 minus y. So actually, the 9s go, and this piece is easy, but that piece you actually don't know how to do. So this is actually, you need to use your calculator. Okay.
ugly cow.
All right. We did a lot today. I'm very impressed. That was good. We got through